The design of beams, columns, or large concrete bridge girders, as shown in these photos, isn't possible without knowing the bending moments and shear forces caused by the loads. Shear and moment diagrams directly show these forces. In this bridge girder, the size of the bending moments defines the number of steel pre-stressing strands that need to run along the girder length. The shear forces define how many steel stirrup bars will be embedded in the webs. At the girder end, where the shear diagram has high values, the stirrups will be close together. Near the middle, where shear is low, the web may not need any stirrups. Now we're going to look at how to easily build shear and moment diagrams to achieve good design of structural components.
Let's look at a simply supported beam. The beam can have any arbitrary loading. I'll draw a distributed load. The value of the load at any point is the load Q of X, where X is the location along the beam. Now we go in and look at a small piece of the beam taken at any point along the length. This piece is cut out at a distance X from the end of the beam. We're going to look at forces on that small beam segment. First, let's define our sign convention for shear and moment. Positive moments cause compression at the top, and positive shears are up on the left side and down on the right. On our beam segment, we have some loading on the top. Since the segment is very short, I assume the loading is basically constant, and the value is Q of X. Next, we draw the possible internal shears and moments on the segment. Since the shear and moment might change from one side to the other, we show the changes D of V and D of M on the right side. The segment has a small length D of X. Finally, we label a point A on the right side. Now we will do some equilibrium calculations. First, the vertical forces must balance. I'll take positive as upward. We have V up on the left, the load Q of X times D of X down on the top, and V plus D of V down on the right. Rewriting the equation, we solve for D of V, the change in shear. On the right side, the two terms V cancel. Then we can see that the change in shear D of V over a distance D of X is just equal to minus the load Q at X. Look at this equation in relation to a shear diagram for the beam. The change in shear D of V over the distance D of X would be the slope of the shear diagram. So, the slope of the shear diagram at any location X along the beam is the negative of the value of the downward load at that point. Let's call this rule number 1. We go back and look at our beam segment again. As a second step, the moment on the segment must be in balance. I'm summing moments about point A on the right side and taking clockwise as positive. So we add in M on the left, plus V on the left times the moment arm D of X, and we subtract the top load Q of X times D of X times its arm D of X over 2, and subtract M plus D of M on the right side. Then we solve for the change in moment D of M by rewriting the equation. The two M quantities cancel out. In the second term, if d of x, the length of the segment, is very small, then d of x squared is infinitesimal, or we can take it as 0. So what we end up with is that the change in the moment, d of m, over the distance d of x, is equal to v, the shear. Now, let's look at this equation in relation to a moment diagram for the beam. The change in moment over the length d of x is the slope of the moment diagram. So, the slope of the moment diagram at any point x is equal to the value of the shear in the beam at that point. Let's call this rule number 2. So, we have 2 rules for building shear and moment diagrams. The slope of the shear at any point is equal to the negative of the load at that point. The slope of the moment at any point is equal to the shear at that point. For the second equation, we know visually that the moment diagram will have a maximum or minimum value when the slope is 0. So, we can say that the moment will be a maximum or minimum when the shear is 0. Now, let's look at the first equation again. Solving for the change in shear, d of v, it's equal to minus q of x times d of x. Let's integrate both sides of that equation between 2 points on the shear diagram, say from x equals a to x equals b. The integral from a to b of d of v is equal to the integral of minus q of x d of x from a to b. The left term, the integral of d of v, is just the change of shear between a and b. The right term, the integral of q of x d of x, is the negative of the area under the load diagram between a and b. This actually gives us a third rule. The change in shear between 2 points along the beam is equal to minus the area under the load diagram between those points. So now let's do the same with the second equation, integrating both sides. The left side is the change in moment value between a and b. The right side is the area below the shear diagram between a and b. So we have rule number 4. The change in the value of moment between 2 points along a beam is equal to the area under the shear diagram between those points. Now let's summarize what we've developed. Rule number 1. The slope of the shear diagram at any point along the length of a beam is equal to the negative of the loading at that point. Rule number 2. The slope of the moment diagram at any location along the length of a beam is equal to the value of shear at that point. That helps us find the maximum moment in a beam because the slope of the moment is 0 when the shear is 0. Therefore, the maximum or minimum moment occurs where the shear is 0. Then we've got rule 3. The change in shear between any 2 points along the length of a beam is equal to the negative of the area under the loading diagram. And finally, rule 4. The change in moment between any 2 points in a beam is equal to the area under the shear diagram between those points. Finally, we can give general rules on how to construct a shear and a moment diagram. First thing we do is we find the reactions on the beam. They usually help define the values of shear at some location. So inspect the beam with the reactions and identify any points on the beam where you can visually define the values of shear. This is easy. On the ends of a cantilever, we know the shear is 0. Over the reactions on a simply supported beam, we know the shear is equal to the reaction. So now we've got a couple points for the shear diagram on the beam. So we plot those known values of shear. Then we know that the slope of the shear diagram at any point is the negative of the loading at that point. So we start by plotting known slopes. Particularly start at points where the shear is known. Finally, we know the change in shear between any 2 points is equal to the area under the load pot, the negative of that area. So we can calculate the shear at other points in the beam by just taking the area under the load diagram. Second, we want to construct the moment diagram. Again, we start by identifying any locations in the beam where the moment is known. It would be 0 at the end of a cantilever. It would be 0 at the ends of a simply supported beam. So we start by plotting those known moment values. Then again, we know that the slope of the moment diagram is equal to the shear at any point. So therefore, we also know that the moment will be a max where the slope is 0. And that's where the shear is 0, since the slope of the moment is equal to the shear. We also know the change in the moment between any 2 points is equal to the area under the shear diagram between those points. So we can use this to find the moment at other points in the beam.